Good morning everyone, Assalamu alaikum. Today we will start chapter 3 where we will learn new concepts of thermodynamics. So our learning outcomes, or by the end of this lesson, we will be able to understand the concept of heat and work, be introduced to the first law of thermodynamics, apply the first law to closed systems, and explain the principle of conservation of energy. So we will begin with a question. What forms in which energy can cross the boundaries of a closed system? So if we have a system, definitely we will have boundaries. So how this energy is transferred between system and its surroundings, or between two systems. So energy can cross the boundaries of a closed system in form of heat or in the form of work. So in simple words, I will tell you about heat, the concept of heat and work. So heat comes from temperature differences or temperature gradient, and work comes from the force acting over a distance. So heat is the form of energy that is exchanged or transferred by a temperature gradient between two systems or between a system and its surroundings. Joules are the unit of heat, as we know. For instance, energy is transferred or heat flows from the hotter body to the cooler when two bodies of different temperatures are brought together. So if we have system number 1 and system number 2. System number 1, its temperature is 30 degrees Celsius, and system 2 having a temperature of 40 degrees Celsius. So the energy will be transferred from system number 2 to the system number 1. Why? Because from the hotter body to the cooler one. So 40 degrees Celsius is higher than 30 degrees Celsius. So system 2, from the second system to the first system, the energy will be transferred because of the temperature gradient or temperature differences. So now we will talk about heat as a path function and specific heat transfer. So in thermodynamics, heat is a path-dependent quantity. So heat depends on the path which is taken from the initial state to the final state, as we studied, as well as the initial and final states or points. So it depends on the path and the states. So the heat transfer associated with the process depends on the path followed as well as the end states. Unlike state properties, also we talked about the state properties, which are point functions like temperature, pressure, internal energy. So all of these are state properties. So they are just depending on the initial and final state or initial and final points. So they are not depending on the path followed or path taken. So heat is opposite of these state properties. So heat is a path dependent quantity. So heat depends on the points, depends on the initial point, final point, as well as the path taken, because it is path dependent quantity. Specific heat transfer. So the definition of specific heat transfer is the amount of heat transferred per unit mass. So also we have a formula for this specific heat transfer, which is Q equals to capital Q over M small, which is mass. This is mass of the substance in kilogram, and Q capital represents the total heat transfer in kilojoule. You should be able to understand that heat transfer Q and the mass are expressed in kilojoules and kilograms respectively. So they should be in kilo, both of them, to ensure accuracy in the final result. So then there is a question: how can you define work? We know that work is energy done because of the force acting over a distance. So work is defined as the energy transfer associated with the force acting through a distance. and the work unit is joules. The work done during a process between states 1 and 2 is denoted by W12. Then work as a path function in thermodynamics. We already know that heat is path-dependent quantity. So work also is a path-dependent quantity, so it depends on the path taken, path followed between two states, as well as the final and initial states. So work associated with a process depends on the path followed as well as the end states, or can be called as a path function. There are many forms of work in thermodynamic systems, such as boundary work, expansion or compression work. Boundary work is commonly represented by a symbol WB. Then shaft work. Shaft work, what it is? It's the work done by a rotating shaft, like in turbines, engines, and fans, etc. Then electrical work. In electrical work, it represents the work done when electricity flows through a wire, or it comes because of the voltage gradient. That's it. Then flow work, and an example for it is pumping water through a pipe into a tank. So it's the work required to push fluid, and we know that fluid is either gas or liquid. So it's the work required to push a fluid into or out of a controlled volume. Then moving boundary work, also called expansion or compression work, is the work done when a gas changes volume in a piston cylinder system. This type of work happens when the piston moves due to pressure inside the system. In thermodynamics, we assume this process happens in a quasi-equilibrium way. So we already studied in first chapter that quasi-equilibrium state is a state which is it's so near to be in equilibrium state, so it's almost in equilibrium state. So a quasi-equilibrium is a very close to be in equilibrium state. So quasi-equilibrium process means the system stays very close to equilibrium, so pressure and temperature are uniform throughout the process. Boundary work is the work associated with a moving boundary. So this is a picture representing this saying. Boundary work. In figure 3, when the piston is free to move, the small amount of work done by the gas is the change in work equals to the force acting over a distance. So the change in distance is ds, and F represents the force. So F multiplied by the change in distance equal to the change in work. So also, if we replace force with the pressure multiplied with area, we can say that the law is pressure multiplied by the area multiplied by the change in distance. So if we also take these two parameters, area multiplied by this change in distance, it will give us the change in volume. So the change in volume multiplied by the pressure. So you should memorize these three laws of the change in work. This means force times distance is equal to pressure times change in volume. The total work done by the gas as it expands or compresses is calculated by the boundary work, WB, equals to the pressure multiplied by the change in volume. This means you add up all the small amounts of work over the entire volume change. So then we know that when the gas expands, or when the gas is expanding, the work will be positive. But when the work is being compressed, definitely the work will be negative. So work is negative when the gas is compressed, piston pushes in, work is done on the gas. Work as area under the process curve PV diagram. So this area under the curve will be equal to the work done. So in a closed system during quasi-equilibrium, either expansion or compression, the work done is equal to the area under the curve. So this is the curve. Under the curve, this area will be equal to the work done. So equal to the area under the curve on a pressure volume diagram. Then in the cycle shown in figure 4, if we shade this area, the network output is shown here. So which is the difference between the areas under curve A and B. Also, I want to tell you something, that in a cycle we will return to the initial point because it's cycle. So we will begin with A, then B, and from B to A, then it will be continued. So formal sign convection, heat and work are directional quantities. So the direction of energy transfer matters either into the system or out the system. So heat transfer Qn to a system and work done W out by a system are positive. So when the system gain, when the energy is going in the system will gain energy, will take energy, so it will be positive because the heat is added to the system. So that's why it's positive. And the work done by a system is positive. We studied in physics that work done by a system is positive and work done on a system is negative. So then heat transfer Q out from a system. So when the energy is going out of the system will loses this energy, so it will be negative. So and work done on a system is negative. Comparison of heat and work. There are many similarities between heat and work. Heat transfer occurs due to a temperature difference, while work transfer results from a force acting through a distance. Heat and work are both transient phenomena. What does transient phenomena means? It means that they are not staying in the system. They are just passing through the system. So they only exist during a process when energy crosses the boundary. Systems never possess heat or work, but either or both cross the system boundary when a system undergoes a change of state. 3. Both heat and work are boundary phenomena. So they are happening on the boundary of the system. Both are observed only at the boundary of the system, and both represent energy crossing the boundary. Both heat and work are path functions. So what does path function means? It means that they are not just seeing or considering the initial and final points. They are also considering the path taken from the first point to the last. And inexact differentials. Inexact differentials means they are path functions. Going to the problems, the first problem, they provided the initial pressure and the initial temperature, and then the final pressure and final temperature, and they ask us to determine the boundary work done during this process. So we know that WB, which is boundary work, equals to the pressure multiplied by the change in volume. So but in the question they didn't give us the volume, but they provided a graph so we can observe what is volume, what is the value of the volume. So they gave us the initial and final volume equals to the same. They are having the same value, so they will be equal. If we will calculate the change in volume, it will be equal to 0, because if we consider for example here is 5, so 5 minus 5 will be equal to 0. So the change in volume is 0, but it multiplied with the pressure, so anything multiplied by 0 will be equal to 0, so there is no work done. Then in the second problem, you can pause the video and solve it, then you can see the solution. So they provided the first pressure or the pressure. They provided the pressure and the initial volume, then the final volume, and then they ask us to calculate the work done by the system during this process. So the work done will be equal to the pressure multiplied by the change in volume. So 0.1 minus 0.04 multiplied by 200 kilopascal will give us 12 kilojoule. Yes. So these are the solutions for. The law of conservation of energy states that energy can neither be created nor destroyed during a process. It can only change forms. In other words, you cannot make energy or destroy it. You can only move it or change its form. Then thermodynamics is a branch of science that deals with the transformation of energy and its effects on the properties of the substance. So it's a science of energy movement. It studies how energy changes from one form to another, or it also studies how this energy changes affect the materials, etc. The first law of thermodynamics is merely one statement of this general law with particular reference to heat energy and mechanical energy. So E in equals to E out. Then the first law of conservation can be expressed the net change as the net change, increase or decrease in the total energy of the system during a process is equal to the difference between the total energy entering and the total energy leaving the system during that process. E in minus E out equals to delta E. A closed system operating in a cycle in which the work is done by the system. So what does that mean? It means that the system uses energy to do something, like moving a piston or running a machine, etc. Energy cannot be created nor destroyed. The mechanical energy must have been provided from some other source. So it's not just created magically. It comes from a source. So then, since it is a cycle, the system will return to the initial state. So if we have a cycle, so it will just it will return to its initial state. Then there will be no net change in internal energy. Why? Because it ends up the same as it started. So it began with the same initial point, then it will just end in that specific initial point. So only another energy involved is heat supplied or rejected in various processes. The only energy in or out is heat, either supplied or rejected. Hence, by the law of conservation of energy, the work done by the system must be equal to net heat supplied to the system. That's it for today.